Welcome to the deep dive. Today we're tackling a really pivotal moment in deep learning history, specifically for computer vision.
Yeah, this one's a big one.
You sent us this research paper, right? The one that really changed how people thought about building these neural networks, especially making them super deep.
That's the one. Kaming He and colleagues at Microsoft Research back in 2015, deep residual learning for image recognition.
Okay, and our mission here for you listening is to really unpack the puzzle they were facing, trying to go deeper.
Yeah, this weird problem that popped up.
And then get into the honestly pretty brilliant idea they came up with to solve it.
Simple, but powerful.
And then see just how much it shook things up across the whole field. The results were kind of stunning.
Oh, definitely. It's a classic case study, really.
Very
Find the
much.
bottleneck, find a clever way through.
All right, let's dig in. So we knew back then, and the field had shown this already, depth is really important for visual tasks. Recognizing objects in pictures.
Absolutely. Deeper networks build up complexity. You start with edges, corners, then textures, parts of objects, and finally, the whole thing. More layers, potentially more understanding.
That hierarchy seems key, and earlier work really pushed that. Go deeper, get better results, seems simple enough.
Right, it makes sense. Each layer refines what the previous ones found.
So the obvious question is, why not just keep stacking layers? If, say, 20 layers are good, why not 50? Or 100?
Well, that was the dream. But just piling on layers ran into serious trouble. For a long time, the big problem was vanishing gradients, or sometimes exploding ones.
Ah, yes, the signal getting lost or blowing up as you go back through the layers during training. Hard to learn anything then.
Exactly. But by 2015, when this paper came out, those issues were, well, mostly managed.
Right, we had better ways to initialize weights, and things like batch normalization had come along. BN really helped stabilize things during training.
Yeah, batch norm was huge. So you could train networks maybe, I don't know, 20, 30 layers deep reasonably well. But when people tried to push even further,
Something else broke.
something else broke. A totally new problem showed up, one that batch norm and initialization didn't fix. And that's what this paper really focused on, the degradation problem.
The degradation problem. Okay. Is that just like overfitting the models too big, maybe?
That's what you'd think. But no, and this was the really surprising part, it wasn't just bad performance on new data.
Mm-hmm.
When they took a network that worked pretty well, say 18 layers, and stacked more layers on top to make it 34 layers deep, the deeper one did worse.
Worse on the test set, you mean?
Worse on the test set, yes. But, crucially, it also had higher training error.
Wait, what? Higher training errors, so the deeper model couldn't even learn the data it saw during training as well as the shallower one.
Exactly, that's completely backwards.
They're totally counterintuitive.
And they showed it clearly in the paper, like in Figure 1 or Figure 4, looking at what they called plane networks. The 34-layer plane net clearly has worse training error than the 18-layer one. Adding layers somehow made optimization harder.
That is weird, because, theoretically, the deeper network should always be able to do at least as well.
Right.
Couldn't the extra layers just learn to do nothing, just pass the input through? An identity mapping?
That's the key insight. If the first 18 layers are optimal, the next 16 could just learn the identity function, HX, H is X. Then the 34-layer net would perform identically to the 18-layer one.
So there's a theoretical floor performance it should be able to hit.
Yes, a deeper model contains the solution space of a shallower one. But the standard training methods, the optimization algorithms like SGD, they just couldn't find that simple identity solution for those extra layers.
It was too hard to learn do nothing through all those nonlinear activations and weight layers.
Apparently so. The optimization landscape must have been really difficult.
Okay, so they're stuck. Depth is good in theory, but adding layers makes things worse in practice, even on the training set. How did they break this cycle?
This is where the residual learning idea comes in. It's really elegant.
Right, explain the core concept.
Okay, so instead of asking a block of layers to learn the entire desired output mapping, let's say the input is X and you want the block to output HX, they change the target. They ask the layers to learn only the difference between the desired output and the input. They call this a residual, S.
So X equals HX minus X.
Exactly. The layers learn FX equals HXX. And then to get the final output of the block, you just add the original input X back. The output is FX plus X.
Huh. So the layers learn the residual FX, and the block outputs FX plus X, which equals HX. The final output is the same desired HX.
Precisely. But you've reframed what the layers themselves are learning.
And the big idea, the hypothesis, is that learning this residual FX is somehow Easier.
That's the core hypothesis. Think back to that identity mapping case where the ideal HX is just X.
Okay.
In the standard setup, the layers have to learn to output X. In the residual setup where HXX, the target for the layers becomes XXXXXX0.
Ah, so the layers just need to learn to output 0.
Right. And the intuition is it's probably much easier for the optimization process to push weights towards producing 0 output than it is to make them perfectly mimic the identity function through multiple complex nonlinear steps.
That makes a lot of sense, actually. You're basically asking the layers, what change do we need to make to the input? Instead of, what's the entire output? Learning a small correction might be easier.
Exactly. Learn the delta. And they even showed some evidence for this later in the paper in Figure 7. They looked at the variance of the outputs of these residual functions, fx.
What did they find?
They found that the responses, the standard deviations of fx, were generally much smaller in ResNets compared to the outputs of corresponding layers in plane networks.
Suggesting they are learning smaller adjustments?
Yeah, supporting the idea that the layers are learning these small residual corrections relative to the identity.
Okay, cool idea. How do you actually build this fx plus x thing into a network? What's the architecture look like?
They used what they called shortcut connections. Literally, connections in the network diagram that skip over one or more layers.
Like an express lane for the input signal.
Pretty much. Specifically, they focused on identity shortcut connections. If you look at their main building block diagram, Figure 2, the input X goes into the stack of layers that compute Fx, but it also takes a detour, a shortcut around those layers.
And then?
And then that shortcut X is simply added element-wise to the output of the layers, Fx. Right. So you get Fx plus X right there.
Simple addition. And the big advantage of doing it this way with the identity shortcut.
2 massive advantages. First, 0 extra parameters. The shortcut itself is just a wire. It doesn't have weights to learn.
Okay, no extra model size.
Second, basically 0 extra computation. Element-wise addition is incredibly cheap computationally.
Right. So you can compare a plane network and a ResNet with the same number of layers, the same widths, the same parameters, and almost identical computational cost, FLOPs.
Exactly. It makes the comparison incredibly clean. Any difference in performance is really down to the residual learning structure itself, not just adding more parameters or compute.
That's smart experimental design. What if the dimensions don't match, though? Like if fx has a different number of channels than x because of convolutions.
Good point. They addressed that too. They said you could use a projection shortcut, typically a 1-by-1 convolution on the x path, just to match dimensions before the addition.
So that would add some parameters and compute.
It would, yeah. But interestingly, their main experiments, especially on ImageNet, found that these simple identity shortcuts were often sufficient. Sometimes they used 0 padding on X if the number of channels increased. But even that parameter-free approach worked well enough to beat the degradation problem.
So the core benefit really came from the residual structure, not necessarily fancy projections.
It seems so. The identity shortcut was the workhorse.
Okay, the theory is elegant, the implementation is clean and efficient. Now, the big test. How did it do on massive data sets? Let's talk ImageNet.
Right, ImageNet. The standard beast back then, 1,000 object classes, over 1 million training images. This was the main proving ground.
So they built plane nets and ResNets, keeping them comparable.
Yep, same basic architecture, same depths, but the ResNets had those identity shortcuts added.
And the results? Plane versus ResNet on ImageNet, did it solve the degradation?
Absolutely, unequivocally solved it. Look at Table 2 or Figure 4 again. The 34-layer plane network. Higher error, both training and validation, than the 18-layer plane net. Clear degradation.
Okay.
The 34-layer ResNet, dramatically lower error than the 18-layer plane net and way lower than the 34-layer plane net. It completely reversed the trend. Both training and validation error dropped significantly.
Wow. So adding depth with residual connections actually worked as intended. Deeper was finally better again.
Deeper was better. And they didn't just stop at 34 layers. Seeing this worked, they went for it. They built ResNets with 50, 101, and even 152 layers.
152 layers. Was that like crazy deep for the time?
Completely unprecedented for ImageNet. By far, the deepest network successfully trained and reported. And here's another kicker.
Yeah.
For the deeper nets, 50-plus layers, they used a slightly modified bottleneck block design, shown in Figure 5. It uses 1-by-1 convolutions to squeeze the channels down before a 3-by-3 convolution, then expand them back out.
Why do that?
More computationally efficient. It reduces the cost of the expensive 3-by-3 layer. But crucially, the identity shortcut still skips over the whole bottleneck block.
Okay, so still parameter-free shortcuts, And this efficiency meant?
It meant that their 152-layer ResNet was actually less computationally complex, had fewer floating point operations, FLOPs, than the VGG networks like VGG16 or VGG19, which were state-of-the-art before them and were less than half as deep.
Deeper and cheaper, that's amazing.
Depth through efficiency, enabled by the residual structure.
And what about accuracy? Did going from 34 to 152 layers keep improving performance?
Yes, consistently. Tables 3 and 4 show clear gains in accuracy as they increase depth from 34 to 50 to 101 to 152 layers. More depth, better results. The degradation was gone.
So what was the final score on ImageNet? The big win?
The big win was the ILS VRC 2015 competition. Their ensemble of ResNet models achieved a top 5 error rate of just 3.57% on the test set.
3.57%, how good was that?
It won the competition by a pretty comfortable margin. But maybe even more impressive was this. Their single 152-layer ResNet model, on its own, already outperformed all previous winning ensembles.
A single model beat the best combined systems from before.
Yeah, that really drove the point home. This wasn't just a small tweak, it was a fundamental step change in capability. Being able to effectively train that deep was the key.
Okay, ImageNet was a huge success, but they also used CFAR-10 for some finer-grained analyses, didn't they?
Right. CFAR-10 is smaller, 10 classes, only 60,000 images total. Good for running more experiments quickly and looking closer at what's happening.
Did they see the same degradation problem with plane nets there?
Yep. Figure 6, left panel shows it clearly. Deep plane nets struggled on CFAR-10 too. It wasn't just an ImageNet artifact.
And ResNets fixed it there as well.
Fixed it there too. Figure 6, middle panel, and Table 6 show ResNets getting better with depth, successfully training models up to 110 layers.
And this is where they did that analysis of layer responses, Figure 7.
Exactly. On CFAR-10, they measured the standard deviation of layer outputs and found those smaller responses in ResNets, supporting the residual learning hypothesis we talked about.
Now, didn't they do something really extreme on CFAR-10, like a 1,000-layer network?
They did, a 1202-layer ResNet. Partly just to push the limits and see if the optimization method itself would break down at that scale.
And did it? Could they actually train it?
Amazingly, yes. They got the training error down below 0.1%, essentially perfect on the training data. Figure 6, right panel. It showed that residual learning, as an optimization technique, could handle even that absurd depth.
Did it actually perform well on the test set?
No. Its test error was higher than the 110-layer model, Table 6. Around 7.9% and 6.4%.
So trainable, but maybe not useful.
Likely overfitting, as they suggest. On a small data set like CFAR-10, a network that deep it had almost 20 million parameters, probably just memorized the training examples without generalizing.
Okay, so ResNet solved the optimization problem for extreme depth, but things like overfitting, especially on smaller data sets, were still challenges.
Precisely. Training was feasible, but making it generalize well was still tied to factors like data size and regularization. It wasn't magic, but it removed a fundamental barrier.
Makes sense. Now, this wasn't just about getting better numbers in classification contests. How did this ResNet breakthrough impact, like, the wider world of computer vision?
That's where you see the real power. The features learned by these very deep ResNets turned out to be incredibly effective for other tasks beyond just saying this image contains a cat. They showed strong generalization.
Like what other task?
Object detection was a major one. Finding where objects are in an image and drawing boxes around them.
How did they test that?
They took standard object detection frameworks like faster RCNN, which used to rely on networks like VGG16 as their backbone for extracting features.
Right, the feature extractor part.
And they simply swapped out VGG16 and plugged in their much deeper ResNet 101 instead.
Okay, using the ResNet features for detection, how did that work out on tough data sets like MS-Cateau?
Huge improvement. MS-Cateau is known for being challenging, lots of small objects, complex scenes. Just replacing VGG16 with ResNet 101 boosted the main performance metric, MAP at 0.95 by 6.0% absolute.
6% absolute gain. What's that MAP metric actually capture again, simply?
Basically, MAP averages the precision, how many of the detected boxes are correct across different object classes and different levels of required overlap between the predicted box and the true box. The at 0.5.95 part means it averages across overlap thresholds from 50% up to 95%. So it rewards both finding the object and getting its location very precise.
Got it. So a 6% absolute jump on that strict metric is pretty significant.
It's massive. It was about a 28% relative improvement. It clearly showed that the better features from deeper ResNets improved not just recognition, but also localization, knowing where things are accurately.
And this success carried over into the competitions that year.
Big time. They basically swept the board in the 2015 ILS VRC and COCIO challenges using ResNet-based systems. They won first place in ImageNet detection, ImageNet localization, COCIO detection, and COCIO segmentation.
Segmentation, too, so outlining the exact pixels of each object.
Yep. The powerful features from ResNets provide a much stronger foundation for all these downstream tasks. The paper mentions in the appendix some other techniques they use for the competitions, like refining the predicted boxes, using context, testing at multiple scales, ensembling models, but the core advantage came from the ResNet features.
Okay, so let's bring this all together for you, the listener. What's the big picture here? What did ResNets really give us?
Well, residual learning was this deceptively simple idea that cracked a really fundamental problem. That degradation issue was a major roadblock holding back progress. ResNets provided a way to train networks much, much deeper than ever before effectively.
It basically unlocked all that potential for learning complex patterns that people thought depth should provide but couldn't actually realize in practice before.
Exactly. And unlocking that depth directly led to breaking records and achieving state-of-the-art performance across pretty much all the major visual recognition benchmarks of the time: classification, detection, localization, segmentation.
And these tasks are really the building blocks for so many AI applications you interact with now, right? Image search, self-driving cars, medical imaging analysis. This work laid a lot of the groundwork.
Absolutely crucial groundwork.
Okay, so just to quickly recap our journey here, we started with that confusing degradation problem, deeper plane networks doing worse, even on training data.
Yep, the counterintuitive starting point.
Then we saw the elegant solution, residual learning. Making layers learn the difference, fx, not the whole output hx.
Implemented super efficiently with those parameter-free identity shortcuts, fx plus x.
We saw it smash the problem on ImageNet, enabling record-breaking depth up to 152 layers, which were depper yet more efficient than previous networks, leading to decisive competition wins.
Validation on the biggest stage.
And we saw how these powerful deep features generalized, driving huge improvements in object detection on COCIO and leading to a clean sweep in the major competitions.
Showing it wasn't just a classification trick. It was fundamentally better representation learning. It just made optimization easier by reframing the problem for the layers.
So as a final thought for you to chew on, think about that 1202-layer experiment on CFAR-10. ResNets made it trainable, solved the optimization puzzle, got near zero training error, but it overfit the small data set.
Right. Training worked, generalization didn't in that extreme case.
So if residual learning primarily fixed the optimization difficulty for extreme depth, what are the hurdles that remain when we want to effectively use these truly massive models? Is it just about needing gigantic data sets? Or there may be other architectural ideas, perhaps building on the spirit of residual learning, still needed to help these huge networks generalize better, maybe learn more efficiently, or handle complexity in new ways?
Yeah, what's the next residual learning level insight needed to unlock the next stage of capability for massive scale? Something to ponder.